Oh, there are no other like okay, then once they go in, and then I was like, no, I'm so definitely not the name. I know,
Okay, so I didn't get a chance to go over derivative and inverse at a point. So we're going to go over both those things today. And then our last section for this unit is tomorrow, log derivatives, log differentiation. And then we'll have Monday and Tuesday to start going over your test, which is basically chain rule, implicit, and these two topics. And then we'll start 4.1 notes Wednesday, give you an extra day to review on your own, and then chapter 3 test next Thursday. Okay, the only thing that I want to talk about Thursday is that I'm also giving an A/B test on that day, but I'm going to have their help session on Wednesday. But Thursday, I also have a meeting at 7:45, so I have a really early help session, like at 7. So just to kind of go over any questions that you guys have. And you guys can join on Teams as well if you want to do that. So yeah, so Thursday's a little bit, wish I able to give you that full time, but I got a meeting at 7:45 and I got to go too. So, but I'll still give you a 45-minute help session in the morning. Okay. But if you feel like that's not a good time for you, I can also make myself available Wednesday afternoon. You know, I come in Wednesday afternoon, or I can maybe do a Teams help session as well to go over any questions you guys have. So I'll give you 2 help sessions, Wednesday afternoon and Thursday morning. All right, so derivative of inverse at a point. Let's go to page 23. So this is not a hard topic, but it does require us to kind of have some visual connection with what's going on. So if we can see it, it makes it easier to see why we're doing these steps that we're doing. Okay. So first, I want us to understand that what an inverse function is. Inverse function is found by swapping the input x and y values. So a function and its inverse will always have their domains and range swapped. So that means if there is an order pair that lives on the function 3, 5, that means there's an order pair on the inverse that must be 5, 3. Okay, so they're always going to be flipped order pairs of each other. And a visual example that we can see is this f of x and this inverse f of x, this inverse function here. So if there's an order pair of 1, 2 that sits here, there must be an order pair 2, 1 that sits in the other. Okay, so let me just kind of do a quick example here. Find the inverse of this function y equal x equals 2. So okay, so the 2 things that we do if we want to find the inverse function, this is just as a connection with what we're really doing. We want to first swap the x and y. And now our y is going to be in a different spot. So now we're going to solve for our new y. So after we swap our x and y, we solve for our new y variable. So in this case, x minus 2 is equal to 6y. Divide both sides by 6. Now my new function is y equals x minus 2 over 6. The way we can write this as is inverse function, this f negative 1 of x equals x minus 2 over 6. This is just a notation to show that I'm now in the inverse function of this f of x. So if I were to insert 1 into the other or insert the 6x plus 2 into the x, everything will cancel out. And what's left is just x. And x is exactly what's left over here. So if I plug one into the other, basically everything cancels out. I'm just left with this y equals x, this kind of this dividing line between the function and its inverse. So there are three ways to say the same thing. G of x is the inverse of f of x. G of x is inverse of f of x. That's another notation for inverse. And then we can also say that if I plug one into the other and the other into the first one, if I get an x as a result from both of those composite functions, then that shows me they're true inverses of each other because they're going to cancel each other out in a way where the only thing left over is just y equals x. So I like to use this chart to kind of help me organize my progress. So I want us to do this here. I want us to show that connection between the function and its inverse along this top row here. So I want us to highlight those order pairs there. So, I mean, it can work for other order pair 3, 1, 1, 3, 5. I'm going to just, for example purposes, I'm going to just show order pair 1, 2 and order pair 2, 1. So we see that obviously they're not the same order pairs, but they do have that that numeric connection, right? So there's an order pair of 1, 2 that lives on the function. There must be an order pair 2, 1 that lives on the other, on the inverse function. So I'm going to write that here. F of 1 equals 2, and F inverse of 2 is equal to 1. Everybody good so far? Now, a function and its inverse has that location connection, but then there's also a slope connection between a function and its inverse. These are obviously not the same slopes, but numerically, they are going to show a nice connection. So let's say, for instance, that the slope at this line, or the tangent line here, is 1/3. I know this is not a great example here, but the slope at the inverse is always going to be the reciprocal of this value. Same slope, same sign, but just the reciprocal. My bad, my bad. I messed up. I meant the top one to be 3. So this is the steeper slope here. This is a slope of 3, and so this slope at the inverse at their corresponding point is going to be 1/3. Okay, so the way that I want us to write this is my first row is going to store their location and their order pair relationship, and then the second row is going to share their slope relationship. So I'm going to say the derivative of f inverse at 2 is equal to 1/3, but f prime of 1 is equal to 3. You guys see that? F prime of 1 is 3, but the derivative of f inverse at 2 is 1/3. Notice that these are not the same locations, but they are at their corresponding points, right? We've established order pair 2, 1. The x value for the inverse is 2. The x value for the function is 1 here. Right? So the way a problem is going to be presented to you is it's going to ask you what is the derivative of f inverse at a. So you have to understand that a that they give you is the x value of the inverse. So I'm going to start here. This is the unknown that I'm looking for. I'm going to work my way around this chart. And by the way, by the time that I make my way around the circle, I'm going to be able to get to enough information to find my answer. So I'm going to use my information here to figure out that first establish my order pair. Let's say my order pair for my inverse is a comma b, which means that my original function must be b comma a. And once I can establish this relationship, I can then find the slope of the f graph at b. And let's say that gave me a slope of n. And once I have that slope of n, then I can turn around and say, well, if this is a slope of n, then that means the slope of the inverse must be 1 over n. So all my work is going to be done on the function side. I'm not going to do any work on the inverse. I'm going to use the relationship to help me establish that my slope must be the reciprocal of the functions. So this is the way that I present it, but the way that the book presents it is that the derivative of f inverse of x is f prime of f inverse of x, which I find a bit more convoluted. So I like to go through this process because I can kind of get everything kind of labeled and visualized, and I can come back to my answer. That's what I'm looking for. I'm always looking for that slope that is kind of hidden from me at the beginning. Okay, so I'm going to use the same process here to kind of show you how I work through a problem. So let's look at example B here. F of x equals x cubed plus 4x plus 2. It says find the derivative of f inverse at -3. So I want to first establish, we make sure we understand this. -3 is the x value of my inverse, right? Which means that -3 is the what of my function? The y value. That's the most important thing here. If you can just keep that clear in your head, then that will save a lot of issues that you may experience. Just understand that whatever x value they give you of the inverse is really the y value of the original. Okay, so I like to kind of establish my bearings here. So I know I'm looking for this. I'm looking for f, the derivative of f inverse at -3. I don't know what this is, but by the time I figure out the rest of my regions, I can figure out what that number is. But I do know this. I know that on the order pair side, my order pair is going to be -3 something, right? I don't know what the y value is, but I do know that this is the x value of my inverse. But I know that -3 is also the y value of my original function. So I'm just going to set up what I know to be true without even looking at the problem. I know that because they gave this to me, I know I can put those things in place. They're pretty good so far. Now, we're going to go back to our function, and we're going to work with this piece here. We're going to figure out this puzzle here. If I know what my y value is -3, can I figure out what the x is? This may require a little bit of kind of trial and error, but it should be a nice, easy number to find. It's going to be a number, an integer close to 0. So you should be able to plug in just a few small numbers, and you should be able to get to your answer, even though it's not factorable. Okay, so we know that -3 is equal to x cubed plus 4x plus 2. We're working backwards a bit. They gave us the y value of my original function, but I'm working backwards to figure out what the x value is. Okay. Are you guys okay so far? Okay, so I think the easiest way to do guess and check is if I just bring everything over to one side, get that 0 to show up. And that way I can just plug in different numbers for x and see what's going to make this work. So I like to start with 0, right? Is 0 going to work? No. 1 plus 4, that's too big, right? 2 is too big. Anything positive is going to be too big. What if I try the -1? -1 minus 4 plus 5 is 0. So through my guess, even though I can't factor this, I can kind of guess my way through, and this should be an easy number to find. So I know that my x value is -1. So I'm just going to put this in here. I know that my order pair is -1, -3 on my function side, which means that it must be -3, -1 on the inverse side.
Okay, so we don't have to find the other two solutions, because there's 3 in that one.
No, we just need to find the integer value that works. Yeah, there may be other solutions, but we only care about the integer value.
Okay.
Yeah, especially without a calculator, and problems like these are usually non-calculated. So if I can find my quote unquote B value, then that means if I can find f prime of -1, then that slope is going to lead me directly to this slope. So if I can figure out what this slope is, I don't even have to touch my inverse function. I can just use that relationship to jump from here to here. Okay. So I'm going to find f prime of x, and then I could get to f prime of -1. So f prime of x should be easy. F prime of x is just power rule. What's f prime going to be? 3x squared plus 4. There's my slope formula. I want to find the slope at -1. F prime of -1 is equal to 3 times -1 squared plus 4, which is what? 7. So imagine this slope is 7. That means on the inverse side, the corresponding point must have a slope of what? 1/7. Yep. That's it. I think where some students get lost is they don't see that connection. So they're trying to do f prime of -3, and that just throws everything off. So you have to first understand that this x value they're giving you is the x value of the inverse, not for the function. Okay, so just understand that, okay, that number is the y value of my function, and that's how I'm going to get started. Okay, any questions? Okay, let's see. This one, some problems don't require guess and check. Some problems we can just solve by hand, but we're going to set this up the same way. We know this is the y value of the function. Okay. If I like to just go through my chart here, if I know that if I can fill my chart up, I can get to my answer. So I know my ultimate goal is to find the derivative of f inverse at 1. And I also know that 1 is the x value of my inverse, which must mean that it's the y value of my original function. So I can just step this up. I can fill all this in without even looking at my problem. I just have to know what that value is. Okay, good so far? Okay, so now how can I use this to help me solve my next step? Good. Make sure that's the y value. Don't insert the 1 into the x, right? Insert the 1 into the y value of your original function. Okay. Now there's only one variable here, so it looks like we can solve this by hand. What if I just square both sides and then I just solve for x, right? So, it's only when you have multiple instances of x where you have to worry about, okay, maybe it's a guess and check problem. But if it's guess and check, it'll be a nice integer value close to 0. But here I can solve by hand. I can raise both sides with 2 as my exponent, raising both sides with power of 2. I can add 8 to both sides. Add 7 to both sides. 1 plus 7 is 8. So take the cube root of 8. What's x equal to? 2. So I'm going to fill this in. I know 2 is the x value of my function. 2 is the y value of my inverse. So if I can find f prime of 2, that slope value numerically will lead me to what I'm looking for, the derivative of f inverse at 1. So before I can find f prime of 2, I first have to find what? F prime of x. Yeah, I got to find my derivative function first. But let me get this ready here. X cubed minus 7 raised to the 1/2. Guess what I need to use if I want to find the derivative here? Chain rule. Yep. Outside times inside's derivative. So f prime. Okay, we clean that up. 3/2 in front. X squared stays above. Make that a square root of x cubed minus 7. Put that to the denominator. And then once you get your derivative cleaned up, I can find f prime of 2. Insert 2 into my derivative, I get 6. And if my slope is 6 on the function side, my inverse side must be 1/6. I did not touch my inverse function at all. I did all my work on the function side, and I just made that connection. Another issue that students have is they think that this is a perpendicular relationship, so they make it a -1/6. So just make sure that you just do the reciprocal, don't change the signs. The signs will stay the same, just the reciprocal. Okay, questions? All right, let's go to page 24. Okay, anybody still need the first page? Everybody good? All right. Okay, the table below gives the values of the differentiable function f g f prime and select the values of x. Let g equals f inverse. So we know there's a relationship here. G and f are inverses of each other. Okay. So actually, they don't give us anything on the inverse side. They just give us something on the function side. But we can still establish everything that we need. So I'm going to create my chart here. I know I'm looking for g prime of 1. I know that 1 is the x value of my inverse, which must mean that it's the y value of my function. So I can use this chart to figure out what order pair is there going to be something comma 1. So what order pair can I find from the table? 2. Yeah. But that's enough clue for me to fill in this chart here. F of 2 equals 1. G of 1 is equal to 2. I've established that relationship. I technically don't really need this, but I just like to go ahead and just see that flip relationship between my function and inverse, which means that if I can find f prime of 2, then this slope will lead me to this slope that I'm looking for. What's f prime of 2? -2. F prime of 2 is just -2. So if my slope on the f graph is -2, that means even though I don't see it, what's the slope on my g graph? Yeah, keep the sign, just flip the numerator denominator. Okay, you guys want to try number 2? Number 2 is it's related, but you can kind of just look at this here. Write the equation for the line tangent to f inverse at 1. So they don't give you anything on the f inverse side, but they do give you the function side. So see if you can find the order pair and the slope for f inverse, then from there write the equation to the tangent line. Actually, we can just pull the information from number 1, right? Let's do two more. Let's skip down to number 13 and 19. And then we can do the next section, which won't take that long. Okay, so 13 and 19 at the bottom here. Is everybody good with this? Okay, 13. Okay, so 13, without even looking at the problem, as long as I know what that x value is, I can put, I know that's the x value of my f function, which means that it must be the y value of my g function. So it's nice because they give that to you and you just fill that in. And these will always match, right? So once I know what the x value is, I'm just finding the derivative of my g at pi over 2. So two-step process here, find the derivative, plug in pi over 2, get a numeric value. Once you get that numeric value, just flip it, and that's your f prime of 3 pi over 4. Okay, you're good with 13. Try 19. 19 should go fast. Okay, 19, you get 1/7. You set up your chart. You know you're looking for, or you know your order pair. So derivative of h prime at 5. Or sorry, this is the function side. So the inverse side of it, we know that since 3 is the x value of my h, And 5 is the y value of my original function. That means 5 must be the x value of my inverse. And if the slope of my function side is 7, the slope on my inverse side must be 1/7. Okay, so we're near the end of learning all the derivative rules. So there's a few more that we'll do today and tomorrow, and then we'll be done with all of our derivative rules. Okay, so let's go to page 25. Okay, so notation wise, the inverse of a trig function may be indicated using inverse function notation f inverse or with the prefix of arc. So whenever you see inverse sine or arc sine, they mean the same thing. Inverse cosine, arc cosine. So just know that they are interchangeable. You're going to see, you may see either or both notations on the AP exam and just know that they refer to the same thing. So I want to go through these trig rules here. This looks complicated here, but really we just have to worry about these three here. If I can figure out arc sine, arc tangent, arc secant, I know that arc cosine, arc cotangent, arc cosecant will just basically take on what we see on the left one, on the left column, but just the negative versions of them. Okay. Now I like to organize this the same way as I do my trig functions here: sine, tangent, secant, alphabetical with C's there, cosine, cotangent, cosecant. Okay. And this also has chain rule built into them because a lot of times whatever is inside your arc sine is not just going to be an x, it's going to be some expression. So we always take care of chain rule involved. So I'm going to just do the chain rule versions of these derivative rules. It's more useful, I think. Arc sine is just going to be u prime over the square root of 1 minus u squared. Our tangent is u prime over 1 plus u squared. And our secant is u prime over the absolute value of u and the square root of u squared minus 1. Okay, looks really complicated, but I want to kind of go through how I memorize these in a bit. But for our cosine, our cotangent, our cosecant, just copy exactly what you see to the left of them, and then just put a negative in front. Okay. All right, let me show you. This is the way that I memorize it. So I'm going to go through these again and kind of show you how I build these from scratch. So what I do is I know that they're all, first of all, with similarities, right? They all have the same numerator. So that's nice. All the numerators are just u prime. Okay. And then the next thing I notice is that all the denominators are just variations of 1 and u squared. I know there's our secant as the s value u there, but it's just basically 1 and they all have 1 and u squared, right? So if we can memorize this middle one, then we kind of just build off the other ones, right? So if we can memorize that arctangent, that's the easiest one, right? No square roots, no minus sign. It's just 1 plus u squared. Okay. Or u squared plus 1. The order doesn't matter. Okay. Now, that's the easiest one. Okay. Now, the most complicated one is the arcsecant. You know, arcsecant looks complicated with the absolute value of u, so I know that there's an absolute value of u there, so I'll put that here. And I know it's complicated because it's, I think students kind of get confused. That's why, like, I see the square root, but how can I remember what order they're in? So this is how I remember it. I know there's square roots involved. I know there's a minus involved. I know there's u squared and 1 involved. But it's u squared minus 1. And what helps me remember that the u comes first is I know that my u's are next to each other. So I like to start there. Okay. Ask the value of u times square root of u squared minus 1. I'll put the u's next to each other. In order to do that, I got to put the u squared first inside the radical. So I put the u squared minus 1. Now, if I can have this pattern in front of me, I know my arc sign is going to be a little bit different. So if I see the u squared minus 1 is first, or u squared is first in that radical, I just have to change that order. 1 minus u squared on the arc sign side. So I start here with the easiest. I build my most difficult one, and I make sure that my u's next to each other. So if I can figure out this pattern, I just know that I have to flip that pattern around to get to arc sign. Okay, so that's how I remember it. Okay, so let's try a couple of these derivative rules. The hardest part is just memorizing the rules. The rest of it is just following it. So I have arc sine or inverse sine of 3x. Okay, what's my u value here? 3x. So I'm just going to focus on that u value. I'm just going to insert into my formula. Okay, so here's my formula. Okay, u prime is up top. What's u prime? 3. Square root of 1 minus what? 9. Good. So now make sure you square both 3 and the x. So that becomes 9x squared. Okay, so applying the derivative rule I find is easy. You just have to know how to memorize and get to the rules. Okay, you guys want to try 2 and 3 and just follow whatever the rule says? Find the derivative, inverse tangent 2x squared, and inverse or arcsecant of 5x. Build the absolute value of 5x. I don't know what x is. If it's a negative or a positive. Well, this is just a derivative formula, so we leave the absolute value in our derivative answer.
Also, you just leave u as it is.
Leave it as it is. Yeah, leave your absolute value of x as it is. Yeah. And whatever if I were to find the derivative at 1, whatever it gets back in return, absolute value of 1 will be 1. So I can clean it up once I find the slope, but I leave the absolute value in my derivative formula. Okay, let's go to page 26. And let's try 11. And if we have time, we'll do 19. So bottom of the page, 11 and 19, page 26. Find equation of tangent line. So find your order pair, find your slope, point slope one. Okay. Okay, 19, we do a little bit of implicit, and then we just solve for dy dx. So our tangent of y is just we find the derivative y prime, or 1/1 plus y squared times dy dx. Anytime we involve y's derivative, we have to attach a dy dx. Natural log of x becomes 1/x, and then just algebraically multiply by the reciprocal to the other side and solve for dy dx. Okay, so you guys have homework from these. I split up 3.3a and b into two separate things, but they're all under the same section in your textbook or for your homework problem. So we'll do that tonight for homework. Tomorrow we'll finish up 3.4 and then we'll start reviewing for our test. All right, come get your phones. And I'll try to get back your quizzes tomorrow. Oh, that's good.